And we're good.
Okay. So, do you see my screen? Well.
Yeah.
Yeah. Okay. So my idea was to go through the current state of ADR, and then to more or less to explain you a bit of the intuition, ideas, and also have a chance to get more synchronous feedback from you guys. So I will walk you through the current state of it, and so please interrupt me whenever you have some questions or concerns or need for clarification. I think that some of you already read it, but let's just take this chance that maybe I provide a bit more information than what is written there. Okay. So just a little bit about the context. Blockchain Reactor is responsible for providing nodes possibility to catch up faster than executing consensus protocol, height by height, effectively by downloading many committed blocks in parallel from set of peers, and then verifying correctness of block and executing them against up. And we also used to call the protocol executed by Blockchain Reactor as FastSync. And the current architecture of the Blockchain Reactor in terms of concurrency is provided with this diagram. So essentially, as you can see, there is quite some number of coroutines. In addition to the fact that we have quite complex concurrency architecture, there is also tight dependency on the switch module. And this all together was actually made writing unit tests and general understanding code pretty hard. And this resulted in several open and closed issues, and also a lot of frustration when people approach this code and corresponding tests. And so idea is to replace this concurrency. So more or less the idea is that we believe that part of the problem is concurrency architecture itself, part is dependency on the switch. So with this ADR, we try to address both of those issues. And the proposed concurrency architecture is this. So it's actually, as you see, much simpler. So in essence, we have entry point receive task at the P2P level, where we are actually receiving messages from the socket. Then we deserialize them into the corresponding message type, which belongs to a particular channel and reactor. And then we are then processing this message. And so as you see here, there is receive task, which then goes into the receive routine of BS reactor, where we actually deserialize the message into the concrete data structure. And then what we propose with this ADR is that we then essentially enqueue those messages to something we call executor, which is then, as part of processing those messages, calling something we call controller. So more or less, so this is what we kind of have in the current architecture, and there is nothing changing there. So more or less, the receive task is happening as part of P2P, and part of it actually calls the receiver's routine to get a message. But then after this, more or less, all processing of FastSync is supposed to happen within executor task. So, and yeah.
Something.
Sure.
In this diagram, the actual Go routines are shown in this oval.
It's actually the other way around.
Routines, and which ones are just.
So these are the task is active routine, and with oval we have just a function which is not active routine. And so you see that receive task is calling the receiver. It's maybe the word here is confusing. It's actually receive function of the blockchain reactor, which is deserializing the data. And the same thing here. Executor task is calling controller function of the blockchain reactor.
So the task is actually implemented as a Go routine in the code.
Yes, in the Go implementation, it's a Go.
Stuff is it's a functional, it's a call, it's a function call. Right?
Yes.
Okay.
Yeah. So the
comment I have is is this receive task only dealing with the messages like the status messages and the block response messages? I'm asking because there are other, in the implementation, there are other Go routines. For example, the ones that are started when timeouts occur.
yes, so the timeouts.
So one that's running from the context of the switch, I guess, when we get the errors from the switch. So there's multiple. So we receive events from multiple Go routines, and all the handles are supposed to send messages to this executor task.
Yes, so it could be that this diagram is too simplistic in a sense, because you're right. There are also timeout related routine, which are supposedly happening as part of executor task or being spawned by executor task, and they are enqueuing also messages to the executor task. And also the switch upon some peer misbehavior can also send a message that the peer should be removed. So somehow idea here is that executor task is entry point from all network related events, if you want. And so there are potentially multiple active routines before executor task.
Right.
And so they could receive messages from multiple peers. We have one receive task per peer. Then we could have multiple timeout routine, happening also in parallel. And then when, for example, the timeout expire, they might enqueue the message to executor task. And also from the P2P level, we could also receive notification that there is something wrong with the peer, like peer, for example, disconnected. So we should remove from it. So we could, so in that sense, the diagram is a bit simplistic, but you can assume that executor task is active routine, which receives, for example, in Go implementation, I imagine that we have multiple channels. And so the executor task would be sitting and selecting on those channels. And then when new information come, then it will process them by most probably calling controller, which will actually take this event and then turn the state into actually a new state.
Right. Okay.
So more or less the controller we call the kind of core business logic of the blockchain reactor or fasting algorithm, which essentially somehow controls everything. It controls when we should send a message and to what peer, when we should trigger a timeout, when we should terminate, when we should switch from fasting node into the consensus mode, when we should remove a peer, for example, etc. So there are a lot of logic which are extracted into this finite state machine, which is essentially a function, which we call controller. And so controller is a passive entity, which is not, it does not have it's not active, so it's not executed on its own. It is being called by executor, which is active task, to do its logic. And the state of the blockchain reactor is managed by the executor, and it's provided, as we'll see, as input to the controller. On the other side, controller is entity which is responsible for receiving and sending messages from and to peers and effectively triggering timeouts. And in addition, it can, as you mentioned, I forgot to mention it here, it can also receive messages from a switch about the peer misbehavior in addition. In this proposed architecture, there is also idea that executor has additional responsibility, which is called peer heartbeat mechanism, which is really like a small protocol on its own but very simple one. And then, therefore, I decided to kind of move it from controller, just not to pollute somehow the controller logic. The peer heartbeat mechanism is very simple. It consists in periodically sending to a peer request for status, where status is what is like a peer current height. And if peer does not respond timely, then this is in this proposed architecture a sign of peer misbehavior, and so it is being removed from the peer list in this case. Now, the benefit of this architecture is that most of the logic is now part of the controller, and as it's simple function, then writing unit tests is much simpler. And so the also important thing is that because of this dependency on switch, having complex networking scenarios in which peer are added or removed was very hard in the current implementation. And so as here it's just a different event, then it's much simpler to have pretty complex scenarios and to more or less write unit tests for it. And on the other side, as most of those Go routines in this architecture were sitting idle most of the time, because they were their job was pretty simple. So like just deciding part of this control logic was just split it between tasks. So they decide, whether they should send a message or trigger a timeout, something like this, and then they wait for a new message to come or timeout to expire. So the intuition is that with this simplified architecture, the performance will not be affected a lot. But this is something which we need to confirm by experiments, but this is just intuition, because we still keep most of concurrency in this receive routine and send. There is also corresponding set task for sending messages, and then what needs to be executed by the controller or executor is relatively simple, just reacting on it. And there are some parts which are still might be worth of extracting into a separate task, but for simplicity, this is not done in this current proposal. But it's marked as something possible like this, and it shouldn't be a problem to do this, I hope. Now, just to more or less, so with this ADR, we try to formalize the model we assume to really capture this fasting as a proper distributed protocol. So in this model, we assume that node is connected to a random subset of all nodes that we call a peer set. And in this peer set, some nodes are correct and some are faulty. And as this is a random set, we actually don't know what is the ratio of faulty versus correct nodes in a peer set. It could even be the case that all peers are faulty. But as we'll see, this shouldn't be a problem from the guarantees we want to provide. Furthermore, we assume that communication between nodes in a fast sync mode is synchronous, which means that if a correct node sends a message to a correct node Q at time t, then Q will receive this message within delta, where delta is a known system parameter. And normally, we choose delta to be order of magnitude higher than the real communication delay between nodes. And therefore, it should hold, let's say, by default, there shouldn't be a problem. In case there is a problem in network, then the only drawback is that we'll remove the node from our peer set. And so it doesn't affect necessarily the overall behavior. But this gives us some, assuming a bit stronger system model for this module, give us possibility to terminate eventually the protocol and switch to consensus mode, because this is a part of the problem we have with the current code, that essentially we don't have any guarantee that it will terminate. And if we have a faulty nodes coming in and sending us, like informing us that they are in very high height, we'll keep trying to get the nodes, and we don't have a guarantee that will eventually terminate. So here the focus was really a lot on this part on testing, but part also on this guarantee that we want to terminate eventually and switch to consensus mode. And then if there is a need to go back to the fast sync mode, then we don't have a problem doing this. So this is also a big difference with respect to current code, that somehow the fast sync was imagined as a mode of operation and not the one-shot thing. Now, in terms of the requirements, fast sync protocol needs to provide, we have three such property. First one is correctness. If a correct node P is connected to a correct node Q for a long enough period of time, then P will eventually download all requested blocks from Q. So this is it should be I hope intuitive enough. Just if we are connected as a correct node to another correct guy, we are communicating synchronously, there are no problem with the network, then eventually we'll get all nodes from Q we asked them for. Then termination, this is something which is kind of tricky a bit to formalize correctly, and this is my current try, that if a set of peers of a node P, which is executing fast sync, is stable, and the definition of stable here is that no new nodes are added to the peer set, but the nodes from existing peer set can be removed. So we still perceive this as a stable peer set for a long enough period of time, then will eventually terminate. So this means that if we don't, so even like with this protocol, if we have all the time new nodes being added to the peer set and advertising always that they are in some bigger height, we might still try to get a message. But if you have a period of stability, then we'll filter out these nodes eventually. So we know either they are really correct and they have a blocks, or they don't have a block, and then they will be removed from a peer set and then will terminate.
Isn't the correctness requirement here kind of a termination requirement? Like it reads like kind of a liveness property that, you know, if you eventually you'll receive everything you requested.
Yeah, you're right. So it's actually, yeah, it could be that there are both somehow the liveness properties. We don't really have here some kind of safety property, really. Yeah, the safety could be that you know, if you download a block from a correct guy, then it's indeed a correct block. So
right. That's I guess that's what I would have thought the correctness one was, that like if we request a block from a correct peer, then it'll be a valid block.
Yeah. So this is probably, it's a good point. So I should modify this. Yeah, correctness should be exactly that. And then probably inside termination, we should move, in addition of just terminating, they should also download the requested blocks. So you're a good point.
Cool.
And the fairness, go ahead, Anka.
So the other question I have, how do we incorporate also the requirement that the fast sync should proceed faster than blocks are produced, right? Because if you keep asking for blocks and they are, you know, you get higher heights continuously because blocks are created all the time, right? We need to make sure we don't take more time than the actual speed of block creation. You know what I'm saying? Because otherwise, how do you stop? How do you terminate?
Yeah, this is a good point. So if I understand well what you're asking, that if we are creating block really in a fast way, then we will never kind of terminate because we'll keep running for trying to catch up. And then if we're not able to catch up,
put in a requirement that the fast sync has to be faster than the block creation. I'm not sure.
This is a good point, but I'm not sure that we can, because it's kind of a property of the network. So I don't know if we can. This is a good point. So I don't know, frankly, how to formulate.
But do we have a bound on how fast the blocks are created, a lower bound? Can they be created every 10 milliseconds, or is there a 1 second, or what?
It can be as fast as network is able to process the.
So technically, there's no, like, we can't really enforce the lower bound. There is, like, from a local configuration perspective, there are timeouts that enforce a lower bound, but there's nothing at like the global level that allows us to enforce that. So in theory, the validators could like adjust their configuration and basically be able to make blocks as fast as the network allows. But presumably because we're verifying, you know, we have like more rounds of communication in the consensus protocol. So we're verifying like at least twice as many signatures. We should be able to show that this would happen, would be faster.
And also important here, the difference why also there is a good intuition why it should be the case in practice is that for consensus we have multiple rounds of communication and they need to go interior over complete network because the validators needs to communicate end to end between them, to reach a decision. In the case of fast sync, we just talk with our peers. So there is no multiple hops of communication. And so this should probably be much faster than talking with a whole network in multiple steps. But we can try to maybe capture this thing. But what I try here more or less to do is that to place this termination guarantee at a peer level. And so this actually means that when you connect to a peer advertise you its height. Then either if you ask to download the block, either peer will provide you the block or it will not. If it does not provide you a block in a timely and reliable way, then you will remove this peer from the peer set. And then eventually you have this relation with all nodes. And so eventually either you will have a 0 peers in your peer set and then you terminate, or there are no pending requests. Like you look at all your peer and say, I learned all I could learn, so then terminate. Now, what you are suggesting here, if I understand well, that somehow theoretically it could be possible that peers are progressing in the blockchain in a very fast pace, that you always have something to learn from them. But in that case, I think this is perfectly fine from the fasting point of view, because then you will just keep downloading blocks because it's still faster than executing consensus.
Right, but in the same time, if, for example, we have an implementation that it's lazy and it doesn't ask for blocks fast enough, it will never terminate. So my point was, it has to be, I don't know.
Yeah, one thing I was, just one point to make regarding this fast sync protocol. For me, the important scenario, which we don't always think about when we think about fast sync, is the one that we might have a correct validator, which actually is lagging behind. And then the current height is blocked because this guy is needed to make a progress, because the faulty guy, 1/3 the faulty guy, just shut down their nodes. In that case, depending on how fast the slowest guy is able to catch up, depends when we'll proceed with the blockchain. And so that's why this fast sync thing really needs to be something which is kind of responsive and really it shouldn't kind of block forever. There should eventually catch up and switch to consensus mode. And no faulty process should be able to prevent, in this case, from correct guy from switching to the consensus mode and then proceeding with. This is something which I think it's kind of critical for me that we have a test case for this. Because if we are not able to prove that in this scenario, a correct guy, which is being weighed by all other correct guy to join the current height and the round and to be part of consensus so we can decide, then essentially we have again termination issue at the consensus level.
Okay, let's move on, Jacques.
Mm-hmm. Sure. Okay. So as I already mentioned, executor is responsible for sending and receiving messages. And so there are four messages we are exchanging as part of fasting protocol: message status request and the response, and message block request and the corresponding response. Message status request, as I mentioned, is imagined to be part of this peer heartbeat mechanism. And so this is under the responsibility of executor. And executor is just having some kind of timer, and then whenever timer expires, we send request, and then we expect response to come. And we'll see that block request and block response are controlled by the controller. If you just look at briefly at what these messages, how they look like, in the status request we have a sequence number, so we know like so we can order essentially request and also remember what is the last request for which we expect status to arrive. And then inside response, we have a corresponding sequence number, request sequence number, and the current peer height. Message block request on the other side is used to ask a peer for a block. And the response contains for a given height block and the commit, which certify that.
Could we go back to the status? Sorry, I was on mute.
Sure, yes.
This is something new?
Yes. Okay. Yeah, I also make assumption.
Is it a message or is it a broadcast? How do you?
Yeah, so I assume here I made assumption which we need to see whether it's strong or not, that we have a possibility to inform our peers that we are in a fasting mode. And if I inform my peers that I'm in fasting mode, then they know that I will start sending them status requests periodically, and they are supposed to provide to reply with a status response.
But how do you do this? I mean, you need another message, right? To say, hello, I'm just coming up, or I need help. How do you, I mean, this is something all new to me.
Yeah, so we do have as part of at least consensus, we do have some kind of info messages, control messages, which are being sent more or less upon every important step. And so I imagine that we could somehow extend this mechanism to also provide information about the mode in which the node is running. But I haven't developed this into the detail how we can really implement this. It's at this point just at the idea level. I'm also not sure whether this is the smartest way to implement this. It's just that it was the simplest in my mind to separate concern a bit. And so it was important that we have these status response messages coming periodically. And so the simplest thing I could imagine was that, for every peer we just trigger a timeout, and periodically when, timeout informs us the time has passed, we send a message and say, okay, now you should send me a response so I know where you stand with respect to your height. And if you don't send me, then
message, the status request message is sent. I mean, we have a list of peers, I guess, the executor level.
The peers, so the peer list is coming from the switch. So we are from the P2P informed what are our peers.
Okay.
And so executor is having this information as part of the state, as you all see.
And how do we use the sequence number?
Sequence number is just that, so we know we remember what is the last status request we have sent. So just we increment it every time timeout expire and send them. And so we expect the status to cover the last sequence number. This is some kind of very simplistic failure detection mechanism where we more or less are doing, we are asking our peer, are you alive? And we have a serial number whenever we ask them, are you alive? And then they reply with the status saying, yes, I'm alive and I'm currently at height 5, 10, whatever.
Okay, maybe we need a bit more detail because I don't understand exactly how this is supposed to work together with the timeouts. And so we send a status request, sequence number 1, we start a timer. When the timer expires, do we send sequence number 2, or we say the peer is gone, it's a bad peer?
So the way how I imagine that this could work is that we send sequence number 1, we start a timer. When timeout expire, then we check, have we received response with the sequence number 1? If we haven't received it, then we signal that the peer is not responsive, so it should be removed. If we receive 1, then we send 2, and we repeat the same.
Okay.
Does this make sense? Huh?
Yeah. Okay.
And we do this for every peer.
Offline again. I'm not sure we need a sequence number. I mean,
yeah, I was just going to say, I think it's redundant because it's basically equivalent to what you have by looking at the peer ID and the block height, right? Because for a given peer ID and block height, you'll only make that request once. I guess unless the peer goes offline and comes back.
but this is status request, it's not block request.
Oh, right. Sorry.
But still, it's still, I think it's...
You're right, yeah. So probably we don't need, you're right, because we are sending the next one only if we haven't received response for the previous one. You're right. Yeah,
and when we receive a response, we restart the timer. I mean, we send another request, restart the timer, and so on.
We could also do it like this.
I mean, we don't process the response on a timer or a timeout because it's really, we need this as soon as possible. We shouldn't wait for 2 seconds or 15 seconds, whatever the timer is.
Yeah, so this is where I was not sure because I thought that maybe, if the peer is really responding very fast, then we can kind of spam him by sending requests every 10 milliseconds. So I guess that's why I assume that this is controlled by the timeout, so that we don't are overloading our peer with the status request.
Yeah, in fact, this is how it is right now. Yeah, we have a time in the implementation. Even in the old implementation, it was the same. We would send every 10 seconds a status request.
Yeah, I guess that we have a trade-off here, whether we want to overload or how fast we want the peer to be responding to us. And the reason why I thought that this one can be timeout based is that this height information is also part of the message block response. And in this case, as soon as we receive a new block, we want to send the next request. And we have information about peer height there. So we don't necessarily need this as part of status, to be as fast as possible. So but this is I guess I don't have strong preference for any of them. I feel that there is a bit trade-off there, but you're right that we can simplify this by removing sequence number at least.
Okay.
Good. Yeah, one important, probably the most important change in this ADR with respect to current version is in this message block response, where requirement here is that in addition to block, we also have a commit which confirms this block. And in Tendermint, as we know, the last commit or commit of the previous block appears in the next block. So for block H, we need block H plus 1 so we can get a commit which proves or certify block for height H. And if I'm not wrong, in the way how we currently store data in Tendermint is actually done in this way. So we store together block and commit. And the reason why this change is that in the current implementation, when you try to verify a block, or actually you always look at 2 blocks, and then the first block is verified by looking at the last commit from the second block. And then in case there is something wrong there, you don't know which one of those 2 blocks is faulty. And so you don't have, you don't know what peer you should blame for this. And this is very problematic from this, again, termination point of view. Because to really be able to eventually terminate, we need to be clear. Our relation with every peer should be clearly either it's good or bad. I'm getting a block from, I ask you for, or I don't receive them. And this block is correct or not. And so if we are not able to know this information, then we'll just, like in current implementation, we just don't blame any peer, or we blame both of them. And then we keep asking this request to other peers. And so in this case, we actually risk that we remove the correct guy, which is, synchronously communicating with us, because the faulty guy made us do this. So this is kind of the major, I didn't know how to do this actually without incorporating this as sort of atomic data. So they come together, you verify block by block, and if it's correct, perfect. If it's not, then we know clearly who is the peer to blame, and then we remove it from the peer list.
Now, could we do 2 blocks at a time in the response instead, or will we end up with the same problem?
I think that, if I'm not wrong, we end up with the same problem, or we don't end up with the same problem. But in that case, I think that for every block you need 2 blocks. So
yeah,
so I think we discussed this before. We had a meeting, Ethan, remember, and we discussed this. The problem is you download blocks twice in this case, because you have to ask for 2 blocks from the same peer, from block n and n plus 1, and then when you move to the next height, you ask for n plus 1 and n plus 2 from the same peer, and so on.
But we wouldn't. I see. Yeah, of course, because you don't know that block is correct.
Right.
Yeah. So it's basically the same problem.
Yeah.
Never mind.
I mean, it's not the same problem. I mean, it's instead of having commit here, you would have block plus 1, right? At height plus 1.
You'd have block plus 1, but you wouldn't know it's correct until you get the next one. And
no,
so
but you use block plus 1, just the commit part, and it's coming from the same peer. Therefore, you can blame that one peer if either the block or the commit from the block plus 1 is wrong.
Well, but then when you get block plus 2, you won't know.
No, but you don't keep block plus 1. You don't keep block plus 1. When you move,
right, you would throw it. Right.
You ask for it again from the
other. Yeah. So either you'd ask for it again, or you'd be in the same boat as the current situation.
Exactly. If you don't ask, right?
Yeah. Makes sense. So, but I guess the problem with this is that, or the problem with the current. Sorry, the thing outlined here is that we're going to end up sending the commits twice. So either we need to some small re-architecting so that we can send the block without the commit, or we just deal with the fact that we send the commit twice.
Mm-hmm. Yeah, exactly. Yeah. The other question is, what happens towards the end of the height of a peer? Because commit will not be there. So let's say I have a peer at height 100, another peer at height 200, and then I ask for block 99.
So the commit is always there, because in order to, so we differentiate between like a local subjective commit and a canonical commit. And so if you're at block 100, it means you saw a commit for block 100, even though there might not be a block 101 that has the actual canonical commit for 100. And so it's possible that the commit you saw is going to be different than what ends up being included in 101. But regardless, you can still provide someone with a valid, plus 2/3 pre-commit for the block 100.
But if my peer at height 100 is in fast sync mode ahead of me, and it reached block 100, I mean, it knows block 100, but not 101. I ask for him for block 100. Will it have the? It will not.
They will not. He will not reply. It's because what you advertise as your current height is only the block you executed.
Ah, right. Okay. Yes. Sorry, I messed up. Yeah.
Yeah, but this is anyway a good point. But very good question.
Sorry.
I haven't said this. So do we have more question regarding this, or we can proceed?
Yes, I wanted to ask. I was a bit confused in an earlier version whether or not we still do reply with blocks when we are in fasting mode. So
I don't know. This is something I haven't really also anticipated here. Or actually, if you look at ADR, the code, we say if you're in fasting mode, you reply to all messages. So this would actually mean that the way how currently this pseudocode is structured, if you're in fasting, you would also help other guys fasting.
okay. So it's the same as we have today.
Yes, but this, I don't have like very good argument why we should do this or why we shouldn't do this. So not clear to me. You know, it seems kind of correct that you help other guys fast syncing while you're also fast syncing. But I don't know.
Yeah, I think that's right. I don't think we need to turn that off, and it's probably going to be limited overhead, right? I mean,
Yeah, exactly. Yeah, we need anyway. We need kind of resource control. This is something which is a bit orthogonal to what we talk here. That anyway, the fast sync need to be restricted to one part of our available bandwidth, and you know, like in general resources. And we need to do this anyway. So, and this is pretty orthogonal to the you know, this proposal and the pseudocode, etc.
cool.
Okay, so the timeout triggers are what controller returns when it expects from executor to trigger a timeout and then to inform controller that timeout has expired. This is something as kind of response to discussion we had before in the context of consensus ADR or consensus reactor ADR, where the question was whether a controller should spawn or trigger timeouts or someone outside.
These are actually scheduling the timeout.
Exactly. Yeah. Exactly.
I think we should try to be consistent there. Trigger should refer to when the timer actually expires. At least in my opinion, maybe there's better language, but I like to think about it as scheduling a timeout and triggering a timeout. So the controller returns something that says, okay, executor time to schedule a timeout, and then eventually that timeout will get triggered, which means, you know, the timer expired, and then the controller will be told, okay, the timeout was triggered.
Okay, fair enough.
Yeah.
Yeah. So now in this current proposal, we just have two scheduled timeouts. One is for response message, and we call them timeout response trigger or timeout response schedule, and timeout termination schedule. And so now finally we arrive to controller, and controller as an input receive. So it's a function. It receives state and the event. State is current state when it's by controller, and event is what has happened in the network. Now this could come, as Anka said, from several sources, but these external events are, you know, captured with this event object, their nature, and then we call controller with this to give us a new state message to send, which signal what message we should actually send or executor should send, and to which peer, and what timeout should be scheduled with a value for timeout, and also some kind of metadata there. And so in this, for fast sync controller, we assume the following event types: event status report, which is generated once message status, event status report is generated once message status report arrives. Then there is event block request in case the message block request arrive. Then we have a block response, which is also corresponds to the message block response. Then we have event remove peer, which is generated by executor to signal that something has happened with the peer at the P2P level, so it should be removed. And we have these two events which are generated by executor once timeout has expired. And so if timeout response schedule as a response to scheduling timeout response, timeout expire, then we have a corresponding event. And in this case, we just say as metadata peer ID and height, because it corresponds to the request sent to a peer for a particular height.
Can I just, from a structural point of view, it's a bit confusing that we have the event enum and then we have structs prefixed with event. I think it would be nice if they don't share the same prefix, I guess. That's my observation.
So how would you well, I mean, this is going to become a yak shaving conversation, but I guess it's kind of important if we're going to continue to re-architect like this. So how would you differentiate them? Call one an event type and one an event or something?
Yeah, that could work. But I mean, what they really are payloads, right? They're not really, I mean, with the event is encoded what type of...
I mean, you can just say block response without event.
Yeah.
But I agree, the event is the event, and then this struct is the data associated with that event.
And do we, I mean, we don't ever even actually, do we ever actually use the enum? We just use the structs, right? And we would like type assert or something?
I use the enums in the code.
You use them, okay.
But
yeah, handle event does it.
I mean, we can put them all in one struct, the event and the block. But
right.
I found it a bit nicer.
Okay.
Yeah, well, it makes for a nice control structure with the switch. So yeah, I would just add a prefix with payload if it really is the payload of the communication. I think that's the most straightforward, and otherwise, just don't use the same event prefix.
I understand all what you are suggesting, that in case there is a message, corresponding message as a payload, we have a message, and not like the.
Well, the problem is that event status report means two things here, right? In the one case, it's a type event, and in the other, it's a type struct.
But the controller receives an event, and then something associated, the data associated with that event. You know, it could be we could call it message.
Yeah.
It doesn't mean it's a message from a peer or anything. It's a message from the executor task.
Right.
Yeah, exactly. Yeah, it's not only, like the executor is creating the event, and so to inform controller that something has happened. And so like in some cases there is really one-to-one corresponding to the message, or close to one-to-one, because we always include a peer from which the message is received. But you can also have, for example, this event remove peer. This is something which is created by executor because the peer disconnected. And in that case, you just say event remove peer. This is a peer ID.
Wait, but the event remove peer struct is never used in the proposal.
We use it inside here.
No, that is the enum. You switch there. That's not the struct.
But I use it here also when after you are handling particular message.
But in that implementation, the struct is never created. Unless I missed something.
No, I think you're right. It's over. Oh no, the event is in this case the enum isn't used because you're switching on the type.
Yeah, right. You're right. We don't use enum. Yeah, we don't need enum. Yeah, sure.
Right.
Oh.
Because you see here that actually we actually switch based on the type. So yeah, enum is.
Yeah, that would be nice to dissect, I guess.
Yeah, that's a good point. Yeah. So what you're saying that actually we don't need enum and that it's just enough to have.
No, definitely keep the enum for readability.
Mm-hmm.
And just as Anka proposed, just make it have some container that holds the event type and the payload, or whatever the message or whatever you're going to call it.
Yeah. I think this will also probably simplify a bit stuff. Good point. Okay. As we are approaching.
Zarko, a quick question: what's the event timeout termination? How? When do we trigger that?
Yeah.
Is generated by executor? How does the executor decides?
Yeah, so it's actually not executor. So maybe I just explained this because we are close to 1 hour. So that the termination timeout will expire soon. So I just explained how it works. So there are several. So simply saying, there are two cases in which we trigger from a controller this event termination trigger. I call it still trigger. And this is like when there are no more peers or when there are no more pending requests. So if I don't have any peer, then clearly, you know, I'm over. So I should terminate. If there are no, I cannot make any new request, you know, and there are 0 pending requests by, you know, sent to other peers, then probably also, you know, it's game over. But I decided here that I don't immediately terminate, but to trigger this timeout. And I remember when I do this, the current height. And if timeout expire and I'm still at the same height and there are no pending requests, then I switch to consensus. So just to illustrate this, so this is the handling part. So if termination timeout expires, then I check, am I still at the same height and the number of pending requests is 0? Okay, if this is the case, then nothing has changed in the meantime, so I switch to consensus mode. And then just to give you a few examples where we trigger this timeout, for example. Just for example here, when we handle status response event. So we receive a status event from a peer, then peer might potentially, committed some block in the meantime. So we could actually send them a new request. So we try to send them request with this create block request message. And if we failed, message is nil. So there is nothing we can actually send to that peer. And the pending request number is 0. So there are no actual requests made to any other peer. And we are also not able to, to create a request. Then in this case, we trigger this, or we return termination timeout trigger. This is one example. The other example is what happens when you remove peer. So if you remove a peer, and after we remove a peer, there are no peer in our peer map or peer set, then what we can do in that case, there are no peer, so then we return termination timeout trigger. And I think there are also here, when we are handling event block response, the same thing, we got a block, we try to create a new request, we fail, then because there are no new requests we can ask our peer, so then we check if is a peer set empty or there are no pending requests we can send. If one of these two things hold, then we also return termination timeout. So I know that this is maybe a bit. So this is something completely new. So in this proposal, what I try to do is to solve this termination issue of fuzzing by relying on a peer-to-peer kind of relations, and in addition on this termination timeout. So more or less we check, do we have some pending request? Do we have someone in our peer list? Then this heartbeat mechanism ensure that eventually all faulty guys are removed from there, and this timeout termination is more or less giving us a sort of a window of time to sort out some transient issues, so we don't terminate, we don't switch too early. And these three mechanisms together ensure that eventually we'll terminate. Does this make sense?
I have to, think about it, and eventually we have to validate this by implementing it. I'm going to be honest, you know, just not to get your hopes too high, the current implementation and the one I'm working on, of course, it's a lot different than what you propose here. In terms of, you know, the messages, we don't have yet that new message, block request and response with a commit inside. There are many places where the implementation diverges from the ADR. So
yeah, I think that this is by definition of ADR. I think this is kind of fine because it's a proposal of a bit different architecture, which is just a proposal. Does not need to be also you know, acted fully upon, or especially like the current implementation, and even also the one you're working on, although it's a next iteration of the blockchain reactor, does not necessarily need to correspond directly to this one. So
and remember, we did that intentionally. I mean, in theory, we could have done the ADR in 2 steps, but it seemed like that was sort of unnecessarily overhead. But we should probably document the state of things better in an issue. But the idea was first stick with the current set of messages so that we have non-breaking, so that we have a fully non-breaking change, but at least we have a superior architecture that we can actually test better. And then once we have all that in place, which is basically the executor controller kind of structure, then we can make a copy of the blockchain reactor with the new message types that will allow us to, like, you know, guarantee termination, and roll that out kind of simultaneously with the old one.
Yeah, there's just last 2 minutes. I just want to, if it's not a problem, I just explain something I don't have yet in this version. I didn't want to, just to make it a bit simpler. The support for sending multiple pending requests at a time. This is something which, as Anka mentioned, might be the reason of bad performance. And so in this current version of ADR, you can find in a branch, we send 1 request at a time to peer. And the change, and more or less whenever you send request for a block, you start the timeout. And so if timeout expire and you haven't received the corresponding block, you remove a peer. Yeah. So the natural extension of this is to support multiple pending requests. Is when I send a request, I actually don't ask for a single block, I ask for a list for blocks. But then it was not obvious how to what we do with timeouts, you know, because we don't want to trigger at the same time 5 timeouts for 5 blocks. This doesn't make sense because, you know, our peer takes time to send us those blocks. And so what we discussed with Anka is the following idea. When I send request for, let's say, K blocks, I only place timeout for the first request in this list. And when I get a new, when I get this block, then I start the timeout or timer for the next block, which is now the first one. So in that case, we are sort of always placing timeout for the first pending request in the list, and we expect that our peer will deliver us block, you know, in this order, more or less.
So, Arko, you said you have this an actual code. Did you run this, or is it just in the ADR, the code?
No, I don't have the code, so it's just the pseudo code.
Okay.
Yeah. But this, I'm working on this version which supports multiple pending requests. It should not complicate the current one too much. It should not, also it doesn't add any new message. It's just more or less replace the single request with a list of requests at multiple places in the pseudocode. And I think also in terms of guarantees, it shouldn't really change anything. And in this case, this will give us a possibility to ask for multiple block at a time, which hopefully should have better performance, at least during a good case. With the faulty nodes, we were convinced last time we discussed with Anka that there are no problem also in a faulty case, because you are always placing the timeout on the first block. So if he doesn't, because in the current implementation, also one of the problem we were having is that faulty guy can actually skip some blocks. It can, you know, ask for one. It tells you, it sends you the last 50, and then you're blocked because you cannot execute the block if you don't have the blocks in a sequence. So the fact that you have, you know, if there is a hole in the list of blocks, you are blocked. And so that's why it was very important that for every request we ask, we place a timeout and say, this is the block you need to deliver, otherwise you're removed. And we then resend it to someone else. And so even if we are asking for multiple requests, we always place timeout on the first one we need, and we asked. And then if the peer does not provide us that block, no matter what blocks it can provide us, in the meantime, we remove it from the peer list.
Yep. Cool.
Okay, so other maybe more questions?
Well, another thing I was thinking just related to this is whether or not we should request, like whether or not a single request could be for multiple blocks. And then we, you know, instead of just getting one block at a time, we could ask for 10 blocks at a time from a peer.
This is exactly what I said right now.
No, but I mean, so that all the blocks would come in a single response.
Ah, okay. Yeah, this is also a possibility. This is even cleaner. This is even cleaner, actually. I didn't know whether this is problematic from that kind of networking point of view, you know, but you're right. Somehow TCP will deal, you know, trunking the data and sending out, etc. So yeah, it's just that then this delta we are assuming is a bit bigger. Timeout is maybe something we need to then take into account.
In maybe in a future iteration of this protocol where we could take into account like the block size, maybe that's something we would consider, because, you know, if the blocks are empty or small, we don't need to do this one block at a time. It's kind of just unnecessary. You know, we might as well get 10 blocks at once if they're all small.
Yes, this is definitely possible. But like both of those stuff, it doesn't affect. I think it doesn't affect at all guarantees or architecture. It's just then performance consideration, which one kind of makes more sense. But.
Okay, cool. I didn't expect this to take so long, but I guess you know, there's a lot of detail in here, and there was still a lot to discuss. So I think this is a valuable session.
Yeah, I kind of wanted also to provide a bit intuition, but there was no time for this. There are I tried to add quite some amount of comments in the pseudocode, and they are now split into these functions. So hopefully it's more understandable. There was a very valid concern in the first version that it was very dense and it was very hard to digest. So please take a look now. I hope that it's a bit more understandable, and let me know if we still need to keep, I don't know, keep splitting it, or I don't know what else we can do to make it a bit more simpler to understand.
Cool. Any other feedback from anyone else? I guess we'll have to have the state sync discussion another time, maybe next week. But if there's nothing else, I'll stop the recording now.